Okay, everyone, welcome to the video lecture for Chapter 11 on the normal distribution. This is a really important chapter in statistics because most of the statistical analyses that we want to do with our data sets are based on the normal distribution. So we've talked about a normal curve a little bit already this semester. Again, a normal curve is a curve, a density curve that describes the distribution of our data, and that curve is symmetrical, meaning that if you identify the average or the mean of that curve, half of it lies to the right, half of it lies to the left. The curve is not skewed, okay, as we talked about in an earlier chapter. So in this chapter, we're going to talk about the characteristics of a normal curve and the known characteristics, I should say, of a normal curve, and how we can use those known characteristics to estimate probabilities of events occurring, or how likely it is for a given event to occur. All right, so first of all, normal curves are referred to sometimes as Gaussian curves. Sometimes you see that term, okay? I don't tend to use it, but you may see it in a textbook or whatever. It just means a normal curve or a symmetrical curve or distribution, okay? These are a family of symmetrical bell-shaped curves. Now, maybe you've heard that term, bell curve, right, in terms of standardized test scores or whatever. A bell curve is a normal curve. The thing about a bell curve is that there are really only two numbers that we need to know to be able to define that curve. First of all, we need to know the mean, okay, and we need to know the standard deviation. Now, up to this point, I've talked about the mean as simply x bar, and I've talked about the standard deviation as s, if you remember. Okay, well, x bar and s, when we talk about mean and standard deviation, refer to a sample, all right? Now, here we see on this slide two different ways to describe, or denote rather, mean and standard deviation. We see mu, which is a weird, almost U-shaped, or a weird-shaped U, I should say, letter U. That defines our population mean, and then we have sigma, which defines our population standard deviation, right? So these two then are for a population. Now, why do we have two different ways of defining mean and standard deviation? Well, think about it this way. Let's say you want to know the average height of all 2 billion adult females, humans on the planet. There are probably about 2 billion people that fall into that category, adult and female. You can't possibly measure the heights of 2 billion people. You simply can't do it. It's just not logistically possible. So while we want to know what that true value is, we can't know it precisely because we simply can't measure the heights of 2 billion people. But we could take a sample of those 2 billion people. Maybe we measure the heights of 10,000 adult females spread across the globe. That's much more doable, isn't it? Yeah. If we take those 10,000 measurements and we average that, then we're talking about a sample mean because it's from a sample of 10,000. We could also, from that data, calculate the standard deviation, which would be S, the sample standard deviation. Those two then, our sample mean and our sample standard deviation, would be estimates of our true population mean and true population standard deviation that we can't know precisely because, again, we can't measure the heights of 2 billion people, all right? Okay. We're going to talk in a later chapter more about the distinction between a population and a sample. But suffice it to say, for now, when we talk about means and standard deviations, we're going to assume it's population. So we're talking about the population mean and population standard deviation, mu and sigma, all right? Okay, here below we have two different normal curves, or bell-shaped curves, all right? Now, here, in this one on the left, they've identified the mean, which is the center, and they've gone out to +1 standard deviation. So this distance here between the mean and that value represents +1 standard deviation. You could also define it as, from here to here as -1 standard deviation, although it's not marked on the curve. All right. that +1 standard deviation represents an inflection point. Okay, it's a point where the angle of this curve changes, all right? Or the slope changes, I should say. All right, over here, notice we have a different curve. It's normal because you see it's symmetrical, but notice that's very tall and narrow compared to this one, which is kind of short and squat. All right, we define this one by two things. Again, our population mean and our population standard deviation. The reason why this curve is more narrow is because the standard deviation in this curve is smaller than it is over here, okay? My point is that if you know what the mean is and the standard deviation, you can define that curve. How? Through this formula. Now, I'm not going to ask you to calculate anything with this formula, okay? Also, for some reason, that square should be over there. It moved off for some reason in the formatting on the iPad. I'm not sure why. But anyway, the point here is that if you know any value of x, any value of a data point along the x-axis, you can plug it in right there on this formula, and it will spit out a function of x, which is a y value, something on the y-axis. So if you had 100 data points that extended from this end of the curve all the way across the x-axis to this end, and you plugged in every one of those x data points right there, it would spit out 100 values of y, which you could then plot, and it would draw that curve for you, okay? So this is the relationship. This tells us the relationship between x and y that would then draw that curve, and you have to know two things. Oh, and by the way, this does also, for some reason, didn't show you the mean. The mean is up here as well in this part of the formula. Sorry about that, not sure what's going on. Anyway, if you know the mean and the standard deviation, which are both up here in this incorrect formula, again, due to formatting, you would be able to draw that curve. Okay, again, I'm not going to ask you to use that formula. I'm not going to ask you to calculate it by hand. This is all done behind the scenes by software when we look to have software calculating or drawing curves for us. Okay. All right. So let's look at one important thing here. I'm going to draw out a density curve. Okay, so let's say we have an x and a y-axis. Okay, and first of all, let's imagine that we have a frequency distribution in terms of a histogram, right? So we've done this before, right? We have a histogram. You can tell that histogram is basically symmetrical, but we could also draw a normal curve, a density curve, over top of that, something like this, right? So that line, that smooth line I just drew, is the density curve for that histogram or for that frequency distribution, all right? We're talking about density curves here in terms of normalized curves. I'm sorry, in terms of normal curves, okay? All right, now, let's say that we have a density curve, and these are kind of hard to draw sometimes, like that, okay? We can define the center of that curve, again, as our population mean, or mu, and we could go out to plus and minus 1 standard deviation. So this distance here would be 1 standard deviation. That would be plus 1. And this distance would be minus 1 standard deviation below the mean. Again, if you know the mean and the standard deviation, you can construct that curve. Those are the only two things you have to know for that, all right? Okay, so let's take a look at a couple of curves here that are very important, okay? All right, so these two figures show you the relationship between the mean and the standard deviation and why you only have to know those two things to be able to draw the curve. So look at these three curves that we have here on top. We have one in blue, one in green, and one in red. But notice that all three of them are centered on 15. That's because the mean of all three of them is 15. All right, they're all centered on the same point. But notice they're all very different in terms of being wide versus narrow. That's because the blue curve that you see here, being the narrowest, has the smallest standard deviation of 2. The green curve next has a standard deviation of 4, and the red curve, the widest and shortest, has a standard deviation of 6. All right, so the standard deviation defines the width of the base of the curve, whereas the mean defines the location on the x-axis of that curve. Look down here. Here we have three curves. Notice they're all symmetrical. They're all the same shape. That's because they all have the same standard deviation of 3, but they're each located at a different average on that x-axis, averages of 10, 15, and 20. So this one's at 10, this one's at 15, and this one's at 20. All right, so those three are different not because of standard deviation. They all have the same standard deviation. They're different because they all have different means. They're located at different points along the x-axis. And that's what I meant. You only need to know two things, the mean and standard deviation, and you can draw any curve. All right, let's look at some examples. So here we have on the right human heights. Okay, human heights on the x-axis by gender. So this might be male or female, not sure which. But if you draw it in terms of a histogram, you can see it's fairly normal. But then put a density curve over top of it, and that density curve describes that very well, doesn't it? It matches up pretty well. So human heights then can be fairly accurately modeled by a normal distribution, that density curve that you see there. On the contrary, guinea pig survival times after inoculation with a pathogen, a data set we've already seen a couple times in this course, cannot, because that data set is skewed. It's skewed to the right. Look at the histogram, right? The boxes, the bars, they skew out to the right. So if you drew a density curve over that or told Minitab to, you would get something that looks like this. That is not a normal curve. That's non-normal, okay? One thing I forgot to mention, normal curves or data sets that are normally distributed are referred to as parametric, okay? So this data set would be considered parametric. The guinea pig data set below is referred to as non-parametric, okay, non-parametric. And this is a really important distinction. Non-parametric is a non-normal or skewed curve, okay? Statistical tests come in two basic varieties. Those that you can run on parametric data and those that you can't and therefore have to run on non-parametric data. So this is why it's very important when you get a data set and you first start looking at it to do, or rather produce a frequency distribution, histogram or whatever, to try and look and see if that data is normally distributed or not. If it's not normal, if it's non-parametric, there's a different class of statistical tests you have to use, okay? If it's parametric or normal, like the human height, for example, then there's a whole other set of statistical tests that we use. We hope our data is parametric and normal because those tests are more effective, we'll just say for the time being. Non-parametric tests are less desirable, but if you have a non-normal or skewed data set, they're your only choice, right? For the rest of this course, we're going to deal mostly with the parametric side of things, the normal data sets. All right. Okay. Next thing I want to talk about is a really important rule regarding normal distributions or normal density curves. It's called the 68, 95, 99.7 rule, okay? Now, again, this applies only to normal data sets or normal curves. If you know the mean and the standard deviation of a normal curve, then you can very easily estimate the likelihood of any given event falling anywhere on that x-axis, okay? All right, so here's the rule. Again, 68, 95, 99.7. What that says is that between +1 and -1 standard deviation, this area here, that should represent 68% of the area of our curve. And remember from chapter 9, areas under the curve represent probabilities, right? Areas equal probabilities. So if we have an event that falls between +1 and -1 standard deviation, then we can say it has a 68% probability of occurring because the area bounded by +1 and -1% is 68% of our curve. All right. What if we went out to +2 or -2 standard deviations? So what is the area between +2 and -2 here? That area is 95% of our curve. So an event, whatever it might be along this x-axis, would have a 95% chance of occurring between +2 and -2 standard deviations. What about 3 standard deviations. What if we go all the way to the tail end of this side, +3, and this side, -3 standard deviations? Now we're talking about 99.7% of the area of our curve. So any event in this data set has a 99.7% chance of occurring between +3 and -3 standard deviations from our mean, the mean being at the center. Okay, so this is really useful. You can apply this rule to any normal curve, okay? It applies, no matter how tall and narrow or short and sort of squat that curve is. As long as it's normal, this rule applies, okay? All right, now we're going to see in a little bit how we can actually get the area of that curve more precisely using Table B, which I passed out during class and which I'll post on Canvas for everyone to have access to, all right? Okay, let's look at an example of how we might use this information or use this rule. Let's look at bone density. So here we have World Health Organization definitions of osteoporosis and osteopenia, and also normal bone density. All right, let's define these. Normal bone density is bone density that is within 1 standard deviation of the young adult mean or above. Okay, young adults, so we're talking people, 18 to 25, something like that. You wouldn't expect them to have osteoporosis because they're young. We know that as we get older, our bone density declines, and eventually you might reach a point where it's so low that now you have brittle bones and you could be diagnosed or defined as having osteoporosis. All right. By the way, these values here, z-scores as they're called, don't worry about those. I'll explain those in a little bit. All right. Okay. So normal bone density is any bone density within 1 standard deviation of the young adult mean or above. What about low bone mass or low bone density? What's called osteopenia. This is bone density that is 1 to 2.5 standard deviations below the young adult mean. All right. What if we have a bone density that's more than 2.5 standard deviations below the young adult mean? Well, now we have osteoporosis, bone density 2.5 standard deviations or more below the young adult mean. All right, so here we have our normal curve for, normal curve for bone densities, right? You see that here. Okay, now I'm gonna explain why this x-axis looks the way it does here in a minute. It's not actually in units of bone density. It's called a standardized curve where the mean bone density is actually placed at 0, okay? You go out to this point, you have +1 standard deviation. Here you have -1, +2, -2, +3, -3. So the x-axis is actually in standard deviation units, essentially. Okay, so look at our definitions above. Low bone mass or osteopenia is any bone density between -1 and 2.5 standard deviations below our young adult mean. That's our young adult mean. Anything between -1 and -2.5 is osteopenia. So it's this area I'm describing right here. Osteoporosis is anything of 2.5 standard deviations or more. So osteoporosis is anything from this point, -2.5 or more away from the young adult mean. So it's this area right here. Not many people fall into that, do they? In terms of the young adult population, because that's a very rare occurrence for somebody who's that young. All right. So, question over here on the right. What percent of young adults have either osteoporosis or osteopenia? All we're asking in this question is what percent of young adults would fall at less than 1 standard deviation or more below our young adult mean, right here. That's the point where osteopenia begins. It runs to here. This is the point where osteoporosis begins, and it goes all the way off the chart. This is asking what percent of young adults have osteoporosis or osteopenia, so it's asking for this area to the left of -1 standard deviation. All right, what percent of young adults fall into that? What is that area, in other words? Well, if you know that between -1 and +1 standard deviations you have 68% of your curve, then that means that the tails on the right, this one and this one, must add up to 32%. 100% minus 68% means we have 32% in these tails. Half of 32% is here, 16%. The other half of 32%, 16% is here. So this area then represents 16%, right? If this is 68%, the two tails in blue and green here must be 32%. We want the area of one tail, so it must be 16%. 32 divided by 2 is 16%. So the answer to this question, what percent of young adults have osteoporosis or osteopenia? 16% of young adults. Okay. All right, that's how you can use the that rule, the 68, 95, 99.7 rule. Now let's look at this in a little bit more detailed way. All right. So here on the top left, you have now two curves. We have a blue curve, which is the young adult mean. I just showed you for osteoporosis, osteopenia, okay, centered on 0. But now we have a new curve, the curve in red. This red curve is for women aged 70 to 79, all right? So on the right, women aged 70 to 79 are not young adults, obviously. The mean bone density in this age is about -2 on the standard scale for young adults. So notice that this curve for elderly women is shifted to the left. It is centered on -2 standard deviations, meaning that the average for elderly women is 2 standard deviations below the young adult average, which you see right there. That's why the red curve is shifted to the left, because as you get older, your bone density decreases, and so you'd expect that curve to shift to the left, right? Or correct? Okay. So the question here then is, what is the probability that a randomly chosen woman in her 70s has either osteoporosis or osteopenia? In other words, 1 standard deviation below the young adult mean. All right, so this is our young adult mean, right? 1 standard deviation would be about right there, and there you see it. That red arrow is at -1 standard deviation. Okay, so look and see where that falls on the red curve, the elderly women's curve. It's if their standard deviation, if their mean is -2 on the young adult curve, then that looks to be about +1 standard deviation on the elderly women's curve. Why? Because their curve is shifted to the left. So if this is +1, that would be -1. That would be 68% of the area of that curve. We have an additional 16% here. 68% plus 16%, 84%. Does that seem to make sense? Does that red arrow look like the area to the left of it on the red curve is about 68% of that red curve? 84% of that red curve. Yes, it does. The red arrow marks -1 standard deviation on the young adult curve, but it's actually +1 standard deviation. That's our mean on the elderly women's curve. That's +1 standard deviation on the red curve. Anything below that represents osteoporosis or osteopenia on the young adult scale. So because the mean of older women is 2 standard deviations away from the mean of young adults, the red arrow also marks, as I said, +1 standard deviation away from the older women's mean bone density, which means this must be 16%. So 16% of elderly women would not have osteoporosis or osteopenia, but 84% would. So this is just another example of how you can use the 68, 95, 997 rule to estimate probabilities. Okay? All right. So now let's talk about the standard normal distribution. So before I talked about z-scores, and I said just ignore the z-score until we get to that point. We're to that point. So in terms of actually using the 68, 95, 997 rule to estimate probabilities on a normal curve, there's a really simple way to do it. We have to do what's called standardization. We have to standardize our data, okay? Now, first of all, again, I'm not sure what's going on with the formatting here when I convert this over to iPad, but this formula is not complete, so I'm going to fill it in, okay? So this is how we calculate z-score. Z equals some value of x that you see right there minus our population mean divided by our standard deviation. So z-score equals x minus mu over sigma, all right? Now, you can take any value of x, like for example, height in inches, and plug it into this formula as the x value, and if you know this, from this curve, if you know what the mean is and the standard deviation, that's our mean, that's our standard deviation, you plug those in, mean, standard deviation, you can calculate a z-score for any given value of x here. All right, why would we want to do that? A z-score is very useful because a z-score is simply the number of standard deviations away from the mean that value of x falls. So take a look, for example. Here we have 67 inches. So for this population of humans, 67 inches represents plus 1 standard deviation from the mean of 64.5. Okay, so if you plug in 67 for x and your mean of 64.5 and your standard deviation of 2.5, right, 2.5, you plug it in, you get a z-score of 1.0. Okay, now again, that's if x equals 67, that's if your mean is 64.5, and it's if your standard deviation is 2.5. Okay, you get a z-score of 1. That means that 67 inches is plus 1 standard deviation away from our mean. All right, what if you plugged in 69.5, which is here at 2 standard deviations? Plug in 69.5, 64.5 there, 2.5 there, you would get 2 as your z-score because 69.5 is 2 standard deviations to the right. What if you plugged in 59.5? Then you would get a z-score of minus 2. Minus 1, minus 2. Minus 2 z-score means 59.5 is 2 standard deviations below your mean of 64.5. So if you do this calculation here for a whole bunch of x values, you convert the x-axis into a standardized height, where 0 is our mean, plus 1, minus 1 standard deviations represent 68%, plus 2, minus 2, 95%, plus 3, minus 3, 99.7%. So by standardizing, you can very easily convert the density curve into one where you can eyeball and estimate very easily what probabilities are of any events occurring. Okay. All right, so let's take a look. So again, I'm not sure why this formula is not showing up, but our z-score equals any value of x minus our population mean divided by our standard deviation. Okay, and so when x is 1 standard deviation larger than the mean, the z-score equals 1. All right. When x is 2 standard deviations or falls at 2 standard deviations larger than the mean, then z-score equals 2. If x were minus 1 standard deviations below the mean, our z-score would be minus 1, and so on. All right. Also, when x is larger than the mean, z is positive. When x is smaller than the mean, z is going to be negative. Okay. All right, let's take a look at an example. Oh, it's still doing this. Sorry about that. So let me fill this in. All right. Okay, so let's look at women's heights again, right? Women's heights are normally distributed. How you would denote this is that it's normally distributed, capital N, with a mean of 64.5, standard deviation of 2.5. That describes that curve right there. So with this information then, what percent of women are shorter than 67 inches tall? Another way to ask that, what is the probability of a random woman height falling at 67 inches or less? That's another way to ask that. Think about it in terms of probability, right? Okay, so if our mean is 64.5, standard deviation 2.5, we have a height of 67 that we're interested in. Plug those into our formula, right? 67, minus 64.5 divided by a standard deviation of 2.5, we get a z-score of 1. So that equals 1. That means 67 as a height falls at 1 standard deviation from the mean. Right there. plus 1 standard deviation. But our question is, what percent of women are shorter than 67 inches tall? Well, if that's plus 1, we know that from plus 1 to minus 1, we have 68%. According to our rule, this must be 16%. So 68% plus 16%, 84%, right? That's just another way of saying that 84% of the area of the curve falls to the left of plus 1 standard deviation from the mean. And that's why z-scores are useful, because they're a measure of how many standard deviations away from the mean some value of x falls, right? Okay, now let's look at table B. So again, I pass this out in class, but I'll also post this on Canvas so you always have access to it. Table B has a lot of information on it. You see all these numbers in the body of the table. Those numbers are areas to the left. Remember that. They are areas to the left of any given z-score. So let's say you have a z-score of minus 2.5. Okay, your z-scores are along the left, the y-axis here. All right, minus 2.5 is right there. 2.50 is our first increment. So a z-score of minus 2.50 would have area to the left of 0.0062. Now, what if you want to convert that to a percent? What percent of the area of the curve is to the left of the z-score of minus 2.5? You move the decimal 2 places to the right, 1, 2, 0.62%. So 0.62% of our curve falls to the left of minus 2.5 standard deviations. All right, what if we have a z-score of minus 2.56? Well, 2.50 is right there. 2.51, 52, 53, 54, 55, 56, 2.56. That would have an area to the left of 0.0052 or 0.52%. So a z-score of minus 2.56 is further to the left of the mean than a z-score of 2.5. So the area to the left of that should get smaller, shouldn't it? And it is. It's 0.52% rather than 0.62%. Okay? So again, all of these values here are areas to the left of a given z-score. All right, so let's take a look at an example here. So let's say we have a z-score of 1, right? The area under the curve to the left is going to be 0.8413. We already decided that was the case. We said 84%, right? If you have a height of 67 inches, that is plus 1 standard deviation. The area to the left we said was 84%. But now let's use the table to confirm that. So that's a z-score of 1. Look up a z-score of 1.0, right? And this is plus 1.0, so it's the second half of table B. The first page of table B is minus z-scores. This is the second page, which is positive z-scores, plus z-scores. Here we have a plus 1 z-score, 0.8413, 84.13%. And that confirms what we found before, 84% being to the left of a height of 67 inches, which is 1 standard deviation. All right. So some points on using table B, and this is going to be one of the last things we talk about here. I'll finish up the rest of this chapter in a second video to come later. So tips on using table B. Because a normal curve is symmetrical, as we said, okay, because of that curve symmetry, there's 2 ways of finding areas to the left of a z-value, all right? Areas to the right of a z-score. We've talked about areas to the left because that's what the table actually gives you, okay? But the area to the right of a z-score can be found as the area to the left of the negative z-score. So if you have a negative z-score, which is to the left of our mean, maybe that's an area of 0.0099, correct? Well, the positive reciprocal z-score, say this is minus 2.33, an area of a z-score of 2.33 would have exactly the same area to the right, 0.0099. So if you have a negative z-score, you want to know what the area to the right of the same z-score is in the positive, you just flip it around, it's the other side. Now, you can also do, and this is what I typically do more often than not, the area to the right of z equals 1 minus the area to the left of z. So let's say we had 16% as an area left of z. You want to know what the area to the right of that is. Well, the whole thing is 100%, right? 100%. So 1 minus the area to the left gives you the area to the right. If this is 16%, 1 minus 16%, or 100% minus 16% is 84% to the right. Okay? All right. So that's where we're going to stop for this chapter. Again, I'll finish up this chapter with a second video lecture to come a little bit later.